So what I want to do today is lay some additional foundations for the discussion of the astrophysical sources. And I want to begin by talking about how one actually computes the propagation of the gravitational waves from the interior of the source where they're generated out through the entire external universe. So I want to imagine I have a gravitational wave source in here. It has some size, some physical size L. It might be two black holes going around each other or colliding. It might be a spinning neutron star. It might be two ordinary stars going around each other. It might be you waving your arms out in space without a spacesuit, so you're going to die in a few minutes. And you wave your arms really hard. But whatever the source may be, it has some characteristic size L. It has some mass m. And I'm going to focus on slow motion sources throughout the day today, as we have in much of what we have done in the recent weeks. And the key thing about a slow motion source is that the reduced wavelength of the gravitational waves is large compared to the characteristic size of the source. And that is true. That is not true of colliding black holes. For a colliding black hole, the wavelength of the waves is comparable to the size of the black holes. But it is true for two black holes that are orbiting each other with a separation big compared to their size. They orbit slowly, and so the waves have a long wavelength, and so this slow motion approximation is valid. And that example illustrates the fact that slow motion sources need not have weak internal gravity. Two black holes orbiting each other, the gravity is weak in between the black holes, but in the vicinities of the black holes it's strong. Another example is a spinning neutron star that's deformed from axial symmetry. It has a mountain on its surface, for example, a 1 centimeter high mountain. And as it spins, that mountain radiates gravitational waves. And the waves are coming from a very strong gravity region of space-time. But neutron stars typically spin sufficiently slowly that the wavelength of the waves is large compared to the size of the neutron star. And as a result, the slow motion approximation is valid. Now, for such a system, it's useful to identify then the location that is a distance lambda bar away from the center of mass of the source. And that's the transition point between the near zone and the far zone. And because lambda bar is large compared to L, and L is bigger than or of order m, in geometrized units, because otherwise because when L becomes of order m, you basically got a black hole, and so the size can never get smaller than about m. And that means that lambda bar is big compared to m, and that means that out at this boundary, gravity is very weak. The Newtonian potential out here would be very small compared to the speed of light squared. Space-time curvature is very weak. So there's some location down inside here where gravity becomes weak. Gravity may be weak all the way into the interior of the star if it's you waving your arms, or into the interior of the source if it's you waving your arms. But if the source has strong internal gravity, then it becomes weak at some location, say a radius of order, say 30 m, so that the Newtonian potential is about 1/3 the speed of light squared. This region between where gravity becomes weak and the beginning of the radiation zone, this region I'm going to call the weak field near zone. The phrase near zone is used in electromagnetic theory for the region inside a reduced wavelength. This is the weak field near zone because I am not allowing myself, when I talk about it, to consider the very strong gravity region, if there is a very strong gravity region. Now, going out into the radiation zone, or the wave zone, beyond this location, I want to split that wave zone or radiation zone up into two pieces. There's a piece that's near the source in which other sources of gravity are unimportant. It's a region then where the radius of curvature of the background space-time, the only source of significant radius of curvature of background space-time is the source itself, not other objects. And so it extends out to a distance that's small compared to the radius of the universe. But if there's nearby stars or galaxies that might produce some significant gravitational lensing of the emitted waves, well, it's got to be close enough that it does not encompass those external stars and galaxies that would do significant lensing. And so I'll put some boundary out here, which is where the source itself dominates the space-time curvature. It's where, as long as you stay inside of here, you can ignore the influence of the gravitational fields of any external bodies. In this region between a radius lambda bar and where you have to cease ignoring external bodies is called the local wave zone. So that region is the local wave zone. And the region beyond there, where external gravity is important, is the distant wave zone. And it has stars and galaxies and black holes that can all influence the gravitational wave propagation through lensing and in some cases through some significant gravitational redshifts or what have you. Now, last week we talked about the geometric optics approximation. And the geometric optics approximation is what we use to propagate the waves out through the distant wave zone so as to deal with issues of the lensing by galaxies and black holes, for example. So out in here, the method of analysis of wave propagation is geometric optics. In the local wave zone and the weak field near zone, gravity is weak. Space-time curvature is unimportant, except for a tiny bit that may be due to the source, but that's a very tiny bit because gravity is weak throughout there. And so to a rather high degree of accuracy, one can use the linearized theory, linearizing around flat space, to discuss the gravitational waves, and also to discuss the transition from the near zone to the radiation zone. That can all be done using linearized theory. If the source itself has strong internal gravity, as in the case of two black holes that are orbiting each other, or a spinning neutron star, then one is going to have to use strong gravity techniques, fully nonlinear techniques, to analyze the source and its immediate vicinity. So you must use the full, or make some other set of approximations. One must use nonlinear theory. One cannot throw away the nonlinearities of general relativity down in that strong field region. Let me just label that strong field region. And so, for sources that have strong internal gravity, you basically have to deal with the analysis of the internal dynamics of the source using strong gravity down in here. Somehow you have to compute something about the gravitational field out in the weak field near zone from the analysis using nonlinear theory. But once you get the field out into the weak field near zone, you can then use linearized theory to propagate it from there out through the local wave zone, and then you can switch over to geometric optics and propagate from the local wave zone off to through the rest of the universe. So that's the general picture, and it's a picture that has been built up basically due to the fact that the Einstein equations are very complex, and if you want to solve them exactly, you have to have approximation techniques to make much progress. So you do an approximation technique out here that's a geometric optics approximation, an expansion, and the reduced wavelength divided by the other length scales that are present in the problem. In the local wave zone, you do an expansion in the metric perturbation, h, which is small compared to 1, local wave zone and weak field near zone. And then in the nonlinear region, the strong field region, you have to do something else, and that's what I will talk about a little bit at the end of the term. What I want to do today is to give you some insight into the transition from the weak field near zone out into the local wave zone. I'm going to derive the quadrupole moment formula by a technique that does not deal with the source, a rather different technique, but a technique that deals with this transition from near zone to radiation zone, and it illustrates what's going on as a near field gravitational field in the near zone. It transitions into and becomes a gravitational wave in the local wave zone. So that's where I'm going for the next 45 minutes or so. Now, let me talk about what's going on in the local wave zone. Going back and touching base with what I did in the first week during the overview of the course. During that overview of the course, I gave this argument based on dimensional analysis that said that the gravitational wave field, or let me talk about it in terms of the trace reverse metric perturbation, out in the local wave zone must be expressible as an expansion in multiple moments of the source. And on dimensional grounds, in this radiation zone, it should go as the mass divided by radius. I'll put a subscript 0 because the mass is the mass monopole moment of the source. And then we argued it should be the mass dipole moment of the source, m1 dot over r. And then there should be a mass quadrupole moment of the source with 2 time derivatives, 1 time derivative on the mass dipole moment, 2 time derivatives on the mass quadrupole moment over r, and so forth. And then I told you that as in electromagnetic theory, so also here, there would be not just the mass moments, which are the analogs of the electric moments of a source in electromagnetic theory. There will also be current moments, which are the analogs of magnetic moments of the source. And so there would be a current dipole moment, S1 dot over R, the current quadrupole moment, S2 dot over R, and so forth. And then I simply told you that the mass monopole moment is the mass, and it can't oscillate, and so it doesn't appear in the radiation field. It will actually appear in h bar alpha beta, but not in the radiation field. M1 dot is the first time derivative of the mass dipole moment, which is the linear momentum, and it can't oscillate, so it won't appear in the radiation field. Though it could appear as if your source is moving relative to your reference frame, a term would appear in here, but it wouldn't oscillate, so it wouldn't be associated with gravitational waves. And the first term associated with gravitational waves is the mass quadrupole moment. Similarly, down here, the current dipole moment is the angular momentum, which cannot oscillate, and so it would not appear in the radiation field. And the first term down here is the current quadrupole moment. And I want to now make those ideas explicit for these 2 terms. I'll talk first about the mass quadrupole moment in a little bit of detail, and then I will just tell you what happens with the current quadrupole moment. So these are the leading order terms you want to remember in an infinite expansion in multiple moments of the source. Okay. So in order to do this, I want to go into now initially, I want to tell you one other thing. That's what goes on in the local wave zone. But you can do the same argument in the weak field near zone. Again, appealing to the analogy with the electromagnetic case. When you get into the weak field near zone, then you should have simultaneously a multiple expansion in powers of 1 over r. These terms all go like 1 over r, first power, because this is radiation. And energy conservation guaranteed that the field must die out as 1 over r, so the energy flux dies out as 1 over r squared, so energy is conserved. But in the weak field near zone, where you're not dealing with radiation, you're dealing basically with a slowly changing field that has the same form as if the source were completely static. It's a quasi-statically changing field. It's changing very, very slowly compared to changing very, very slowly in the sense that retardation across the source is totally unimportant for a slow motion source. In that weak field near zone, then the expansion is going to be in inverse powers of r as well as a multipolar expansion. And so what we expect from our electromagnetic intuition plus dimensional analysis is this should go like m naught over r, and m1, the mass dipole moment over r squared, and m2 over r cubed, and so forth. And it should go like s1, which is the angular momentum, it's the current dipole moment, over r squared, and s2 over r cubed, and so forth. So that's how it ought to go. So what I want to do is begin by talking about the explicit form in the weak field near zone that corresponds to this order of magnitude discussion, and then talk about the transition into the wave zone and how that weak field near zone field, say for the mass quadrupole moment that dies out as 1 over r cubed in the near zone, how does that convert over to a radiation field that has 2 time derivatives on the mass quadrupole moment instead of none out in the radiation zone 2 and in the near zone none. But it goes like 1 over r in the radiation zone instead of 1 over r cubed. So this is what you would call in electromagnetic theory the induction zone field, sometimes you would call it. How does the induction zone field transition over to and become the radiation zone field? So that's the question. So let's look at the weak field near zone. In the weak field near zone, and in the local wave zone as well, the equations one has to solve are the Lorentz gauge equations. And the Einstein field equations, which is box h bar alpha beta equals 0 in the vacuum. But if it turns out that the source has weak internal gravity, and that's a useful case to consider just in order to help get oriented, then this would be minus 16 pi times T alpha beta, where that's the stress energy tensor, if we have weak internal gravity, so we can extend the analysis into the interior. But if you have strong internal gravity, we cannot, by these techniques, even treat the interior. All we can treat is the vacuum equations in the local wave zone and the near zone, and consider how they're connected. Now, in this weak field near zone, the time derivatives are unimportant. because everything is changing quasi-statically. And so these equations reduced to h bar, we have only spatial derivatives here, not the temporal derivatives. So this beta comma beta will become a j comma j, just spatial derivatives. It's a spatial divergence. So we'll say h bar 0j comma j must vanish. H bar jk comma k must vanish in the weak field near zone. And it says, of course, box h bar 0, 0 is assuming that that the interior of the source has weak gravity. It would be minus 16 pi. T00 would be the Newtonian mass density if this is a weak gravity source, something like you waving your arms, or the sun or the solar system. And box h bar 0j would be minus 16 pi rho vj, where vj is the internal velocity. That is, this is the momentum density of the source. And so the source, I imagine, is you with some mass density moving your arms, or pulsating sun, but the mass density has some velocity v, and it has some momentum density rho v, and that's what the source term is on the right-hand side. It's the T0j source term on the right-hand side. In this weak field near zone slow motion. So there are two assumptions, slow motion and weak field. And outside the source, this is just 0 on the right-hand side. Okay. So those are the equations that have to be solved. Oh, the other thing I need to say is that this wave operator, which is minus the time derivative squared plus the Laplacian, that will just reduce to the Laplacian because the time derivatives are unimportant. So that's Laplacian acting on the trace reverse metric perturbation. So this is a static problem. It's like electrostatics. It's gravitational statics for weak gravity. It's very slowly changing sources. And let's just look at h bar 0, 0 in the weak field near zone. H bar 0, 0 is unconstrained by the gauge conditions. It's only constrained by the field equations. These field equations are just the standard Newtonian field equations, aside from a factor of -4, because h bar 0, 0 is equal to -4 times the Newtonian potential. So let me write that down. H bar 0, 0 in this weak gravity slow motion situation is -4 times the Newtonian potential. And the solution for the solution of that wave equation is that h bar 0, 0 then is equal to 4 times an integral of, this is at some location x, is 4 times the mass density at location x prime divided by x minus x prime d3x prime. So that's the usual 1 over r Newtonian gravitational potential, aside from a factor of -4. My gravitational potentials in Newtonian theory are negative. It's my convention. Okay. And so aside from a factor of -4, it's just the Newtonian potential. Now, I'm going to remind you how you turn this into a multipolar expansion. But I'm going to do it in Cartesian coordinates. The key thing is that let me go do it down here. 1 over x minus x prime is something that I want to consider where x prime is down here inside the source. Let me redraw the source here. So x prime is a point inside the source, and x is a point that is outside the source. It's the field point. And x minus x prime is the distance between them. And the center of mass about which I will do my expansion, I'll put the center of coordinates at the center of mass. Center of mass is close to x prime, but much farther from x. So x itself, the magnitude of that, which I will call r, This is the distance between this field point and the center of mass. This is big compared to r prime, which is the magnitude of x prime. It's the distance from the center of mass to the source point. 1 over x minus x prime is 1 over the square root of x minus x prime squared. So that's 1 over x squared is just r squared. Then I have minus 2x dot x prime, and then I have plus r prime squared. It's useful to introduce a unit vector pointing toward the field point from the center of mass. And that unit vector I'm going to call n, and that's equal to x over r. And so it then is useful to rewrite this x as being equal to n times r. And it's useful to factor out the r squared outside of the square root and rewrite this then as 1 over r square root 1 minus 2 n dot x prime. And then there was 1r here, and I divided out in r squared, so this goes like 1 over r. And then I have plus r prime squared over r squared. That's just simple algebra. And now since r is big compared to r prime, and the magnitude of r prime is the same as the magnitude of x prime, this term is small compared to 1, and that term is small compared to 1. And so I can do a power series expansion of this square root, treating these two quantities as small. It's basically an expansion in 1 over r, the distance to the observation point, to the field point. And so that becomes 1 over r is the first term. The second term you can sort of do in your head. You get a factor of 1/2 when you expand a square root in the denominator. This minus sign becomes a plus sign, so it is plus. The 2 gets canceled out, and it is n dot x prime divided by r squared, just by r squared, because there's a 1 over r from here, and then when that gets expanded out, you get this 1 over r. Okay. And then I'm just going to tell you what the third term is. The third term comes in part from here and in part from the square of that term. The third term becomes, let me write these things in index notation. That makes it simpler. So I'm going to put an nj xj prime. It'll be an nj nk minus 1/3 delta jk. I'm sorry, it's not the way I want to write it. Let me write it explicitly. I'm going to write it as nj nk xj prime xk prime minus 1/3 r prime squared divided by r cubed. It's the next term. And then there's a factor of 3/2 out in front. So that's a little calculation you can do for yourself and see that that's what the answer is. Okay, all I have to do now is feed that back into this integral, and I have h bar 0, 0, which is minus 4 phi, is equal to 4 times the integral of rho over r, that's this first term, it's rho at x prime over r, d3x prime, plus the second term is going to be 3/2 rho at x prime, and then I have, I'm sorry, I want the second term, it's 1, and it's, and let me put the nj over r squared out in front. Let me put this 1 over r out in front. Okay. So the first term, the 1 over r is out in front, and I just have an integral of the mass density. The second term I've pulled out the nj over r squared and put it out in front. And I have a row at x prime, xj prime, d3x prime. In the third term, I'm going to have pull out 3/2. How do I want to do this? Let me write this quantity here as delta jk nj nk. The reason I'm going to write it that way is because this quantity is 1, because n is a unit vector. So all I've done is multiplied by 1. But that will now enable me to pull this nj nk and that nj nk out from under the integral sign. Okay. So I have a 3/2 nj nk over r cubed, and then an integral of rho at x prime times, I have xj prime xk prime minus 1/3 r prime squared delta jk d3x prime. So that's what I get by just putting back in my power series expansion for 1 over the distance between the source point and the field point, put it into the standard integral for the Newtonian potential. Now the first integral here is just the integral of the mass density, and so it's the mass of the source. The second integral is the mass density multiplied by position, and so that's the mass dipole moment as promised. And I use the notation ij, a script ij, for the mass dipole moment. So this is the thing that I called m0 in the discussion over here. That's the thing I called m1 in the discussion over here. So that's the mass dipole moment in explicit notation. This is the mass quadrupole moment, ijk. It's the second moment of the mass distribution with the trace removed, if you think about that. This is removing the trace. Remember, we defined the mass quadrupole moment to be the second moment of the mass distribution with the trace removed. That's the thing that I have called before ijk. And so the final answer is that h bar 0, 0 is equal to minus 4 phi, is 4 times m over r plus ij nj over r squared plus 3/2 ijk nj nk over r cubed. And then there are higher order terms that I could easily have computed just by expanding this square root to higher order. So you can easily generate the entire series in this manner. So this is the way, if one uses Cartesian coordinates, one can talk about the multiple moments of the source. You're accustomed in electromagnetic theory to do it in terms of the spherical harmonics. In here, the dependence on location, on direction, which would be carried by the spherical harmonics, appears in the scalar product of a unit radial vector with the mass dipole moment. So, for example, if the mass dipole moment points in the z direction, so if I is equal just to iz, ez, so it points only in the z direction, then this term ij nj will be iz nz, but nz is the projection of the unit radial vector on the z-axis, so it's cosine theta, where theta is the polar angle. So this is iz cos theta, and you recognize that as the Legendre polynomial of order 1 coming out. Similarly, if you look at this quantity, this ijk, nj, nk, the fact that ijk is trace-free tells you that when you rewrite this in terms of spherical harmonics, it will involve spherical harmonics of order 2. It'll involve things like, well, this term here, if you multiply it by 3, and if you had only the z component, you'd have something like 3 times the cosine squared theta minus 1, which is the Legendre polynomial of order 2. So you sort of recognize the kind of familiar spherical harmonics, but done in a different notation. This notation is very powerful in general relativity because it carries the angular dependences by means of indices on tensors. And you need indices on tensors anyway in order to deal with gravitational wave fields. And so the indices on the tensors do two jobs for you simultaneously. They can take care of the multipolar decomposition by means of indices on tensors, but they also can take care of issues of the tensorial components of the gravitational wave field. So that's the reason that this kind of notation is used. Historically, this is the way spherical harmonics were done in the 19th century. And I think it was probably Felix Pirani around 1950 or in the 1950s recognized that the 19th century way of doing spherical harmonics was ideal in the way it meshed with general relativity. And he introduced this, and this has really caught on. And so a large fraction of the community that works in relativity does spherical harmonics in this 19th century manner for this reason. Okay. Any questions? Okay, so this is the form of of h bar 0, 0 in the near zone. And in fact, this is the only place that the mass quadrupole moment is going to show up, because in these field equations in the near zone, if you look at the field equations written, say, in this form, I should say that you would also have del squared h bar jk would be equal to 0 at the Newtonian order, because in Newtonian, well, let me start over. It would be of order rho v squared, and so it would be very small compared to either of these terms. Okay. And so in the slow motion approximation to the order that we're working, you would have del squared h bar jk would be 0. The only place that the mass moments will appear is up here. The only place the current moments will appear is down there, because this is the current, the mass current. And so the current moments will appear in h bar 0 j in the weak field near zone, the mass moments in h bar 0, 0. And it turns out, when you do this very carefully, that in fact, even if you have a strong source, that in the weak field near zone, h bar jk can be made to vanish outside the source by an appropriate adjustment of gauge. And so, but that's a somewhat subtle issue, which I can point you to reading on. Okay. And so the mass moments show up in the weak field near zone in h bar 0, 0, the current moments, the moments of the momentum distribution in h bar 0 j. So if we want to see how the mass quadrupole moment feeds into and generates gravitational waves in the local wave zone, we have to begin with h bar 0, 0 and figure out how to get from h bar 0, 0 that is that has a form for the mass quadrupole moment, that has this form. How do we get from there to an hjk transverse traceless that has that form? So we've got a time-time component of the trace reverse metric perturbation in the near zone. Somehow must, as you transition into the radiation zone, produce a space-space component in which the two of the factors of 1 over r have been turned into two time derivatives. And so the question is, how does that happen? And the answer is, if you approach it right, is really very easy to see. So I'm going to focus only on the mass quadrupole term. We already know that these terms are not going to produce radiation. So the mass quadrupole term and I want to look at that mass quadrupole term, and what I need to find is I want some expression for h bar alpha beta that is valid throughout the weak field near zone and the local wave zone. So I need an expression that will work from here all the way out into and through the local wave zone. Which means when I make the transition from the weak field near zone to the local wave zone, I can no longer ignore time derivatives. But I can use linearized approximation to general relativity. And so the relevant equations are that h bar alpha beta comma beta is equal to 0, the Lorentz gauge condition, and box h bar alpha beta must vanish. So those are the equations I must satisfy. And I need that in the weak field near zone, I need that h bar 0, 0 is this 4 times 3 halves, so it's 6 I j k n j n k over r cubed at radii small compared to lambda bar in the weak field near zone. So I need a solution of these equations that has this, if you think of it as a boundary condition at small radii in the weak field near zone. What I want is an outgoing wave solution. I don't want standing waves. I don't want ingoing waves. I want an outgoing wave solution which reduces to this form in the weak field near zone. Okay. Now, I'm going to simply write down the answer. It's a very simple answer, but I want to motivate it because I want to tell you something that you probably already know. So this is a side remark. If we want to solve the wave equation, box psi equals 0 for some scalar field, there is a simple solution that is well known. Psi is equal to some function of t minus r divided by r. That's a monopolar solution. Okay. And you can just plug that in and verify that that satisfies the wave equation. Now, the component we're working in Minkowski coordinates or in a Lorentz reference frame. So the components of h bar alpha beta are h bar 0, 0, h bar 0 j, h bar j k, where these are Cartesian components on the j and the k. And the wave equation in Cartesian coordinates, working with Cartesian components, it has the same form mathematically as the scalar wave equation. That is, in these, in our Lorentz frame, using Cartesian coordinates for the space, box is just equal to minus dt squared plus d by dx. Let me write it just with subscripts. dt squared, the time derivative, plus dx squared plus dy squared plus dz squared. So it has mathematically the same form as for the scalar wave equation. In other words, the components in a Cartesian coordinates of a Lorentz frame, the components of h bar satisfy a scalar wave equation one by one, and there's no coupling between them. Okay. So this acting on h bar alpha beta is equal to 0, just a simple wave equation for each component of the trace reverse metric perturbation separately. That means then that the following is actually a solution of the wave equation. I'm going to write down what I need, and then I'm going to discuss it. H bar 0, 0 equal to 1 over r ijk of t minus r, that's a solution of the wave equation. That's not what this is going to be, because that has two free indices. So that can't be the form of h bar 0, 0. However, if I take this and I get rid of these indices by just differentiating partial derivatives with respect to j, xj, and xk, this still satisfies the wave equation. And it's an outgoing wave, because this is t minus r, satisfies the wave equation. And it has no indices left. And if I just look at what this is, if I just look at what this is in the weak field near zone, it turns out if I put a factor 2 on here, then at radii r that are very small compared to lambda bar, at very small radii, I want each of these derivatives to act on the 1 over r. Okay. Because if I act on the 1 over r, I get a 1 over r squared, a 1 over r cubed. Every time I differentiate this 1 over r, I get a term like 1 over r. If I differentiate this guy, I get a term like 1 over lambda bar. But lambda bar is big compared to r. So what I'm saying is that 1 over r comma j is of order 1 over r squared, but ijk of t minus r comma j is of order ijk over lambda bar. But that quantity, because lambda bar is big compared to r in the local wave zone, in the near zone, lambda bar is big, this guy is small, this guy dominates, because it has the small factor of r in the denominator. Yeah. Okay. If I put, I'm not saying it right. If I take 1 over r times ijk and I differentiate this guy, I get 1 over r squared times ijk. If I take this guy and multiply by the 1 over r, so I'm differentiating this one, then I get ijk over r and over lambda bar. The statement is that this thing here is big compared to that thing there. Okay. And so I only want to differentiate in the local wave zone, in the weak field near zone. At small radii, I differentiate this to get an answer. When I do that, I wind up with, the first time I differentiate 1 over r comma j gives me a minus nj over r squared, that is a minus xj over r cubed. It's the same thing. When I differentiate the second time, I get, differentiating this guy, I get a minus delta jk, then minus 3 over r cubed minus 3xj xk over r to the 5th. This delta jk contracted on the I gives 0 because the I is trace free. And so I just get my xj xk over r to the 5th. It's minus 3 nj nk over r cubed. And that's the thing that I would get multiplying back against the ijk, and I wind up in the end, having gone through that mathematics, with just the form that I want for h bar 0, 0. Okay. Yeah.